All right, it is 9 o'clock. My name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking the time out of your busy schedules to join us for Understanding Mass Flow 101, presented by Eric Heilveil of Siemens. Eric is going to talk a little bit about how mass flow meters operate, applications for mass flow, the difference between volumetric flow and mass flow, why use a Coriolis flow sensor, and then recent improvements in Coriolis flow technology. Eric is Siemens Flow Product Manager, responsible for Coriolis, magnetic, and vortex flow product lines. He brings more than 20 years of experience in flow measurement, working with a variety of process instrument companies as an account manager, a product manager, and engineer. Eric's been with Siemens since 2005, his bachelor's degree from Temple University and a master's from Drexel. With that introduction, I'm going to turn it over to Eric. Before I do, though, all the phone lines will remain muted throughout the presentation. There is a question box as part of the control panel that comes with GoToWebinar. Please type your questions into that question box, and I will stop Eric, and we'll get your questions answered. With that, I'm going to turn it over to you, Eric.
Well, good morning. Hi, this is my last time I'm going to say this. Are you clear? Can you hear me?
Perfectly.
Fantastic. Well, good morning, everybody. My name is Eric Heilveil. I work at Siemens. I'm located in Pennsylvania, and with an interview like that, I sure as heck sound a hell of a lot smarter than I think I am. But with that said, what I would like to emphasize is that if you have questions, please do not wait until the end. Go ahead, type them. Mike will interrupt me, and I will be more than happy, actually quite ecstatic, to answer your questions during the presentation. I always feel it's more important to answer your questions than to try to race to get to the end here. There are not a whole lot of slides, so there is a whole lot of room for questions. So without further ado, let me start off my manufacturing on the skids, specialty Coriolis meters to the rescue. As you can tell from the title, the focus of our Coriolis meters currently is on the skid manufacturing, chemical, petrochemical, fine chemical. Actually, food and beverage is currently into a skid, utilizing skids for small process to large process applications where the Coriolis meters are installed and then the skid delivered to the manufacturer. But more on that in a few moments. Siemens is responsible for a host of products in the quote-unquote process instrumentation section, and those products are seen here starting, and I will do this very quickly because this is the boring part, with the level products, of which there are ultrasonic and radar level, weighing products. So this is also a mass flow, but this is the bulk mass like cement, rock, gravel, dirt, where we use load cells, belt scales, etc. Chart recorders, this is the modern versions of the old style chart recorders. Displays, of course, worldwide support and service. Controllers, this is an older variant of a product made by a company called More Products, which is in the building I'm currently located. Positioners for your valves. We don't make valves, but we do tell your valves where to go and how to get there and how fast. Temperature, pressure, and of course, the best of them all, flow. And here you can see our Coriolis line, our vortex, magnetic flow, and ultrasonic. And of course, the very top of the pyramid here is the stuff we're going to be talking about today, which is Coriolis flow. So Coriolis flow, there are an awful lot of questions about what it is, why it is, what's the big deal, what does it do, how does it do it. And just to give you an idea of the reason everybody's asking these questions, that is that Coriolis flow technology is an in-situ system. In other words, it allows for direct integration into the system without sticking anything, interrupting the flow. It's just a piece of pipe. And it provides the most accurate flow measurement technology of the day, 0.1%, sometimes even better, of rate flow measurement. So it's a very, very accurate means to measure flow. Coriolis technology also offers the ability to measure temperature. And the reason they do that is the temperature range on these Coriolis devices can be quite extensive. Some go down as low as -100, -150 degrees Fahrenheit. Some go as high as, specialty meters of course, go as high as 400 degrees, 500, 600, 700 degrees Fahrenheit. So the temperature has a significant effect on how the Coriolis tube vibrates. And because of that, they need to monitor temperature quite closely. Interestingly, is then the temperature can be used as an output. So you can buy a Coriolis meter that measures your flow rate and use the temperature output as well. So you get 2 meters there. Now, the Coriolis flow meter provides a direct mass measure, which is another reason it's important. It does not matter whether you're measuring a pound of rocks or a pound of helium. It does not matter whether the temperature is high or whether the temperature is low. A pound will always weigh a pound. So Coriolis is the direct mass measure. It's not dependent on a pressure reading or a temperature reading for correction. Even though the temperature sensor that I just mentioned, that allows for the meter to confirm that the tube is vibrating appropriately at that temperature. But the mass is the mass, and a pound does not change just because it gets hotter. Coriolis also provides, and we'll get into this in a bit, a real-time density measurement. And so you can actually tell the density of the fluid in the pipe by the frequency of the tube. The faster the tube vibrates, the lower the density of the material. So you can imagine if there's a flow tube and it's vibrating and it's empty or just has air in it, it'll vibrate much faster than if you filled it with liquid mercury. That would be slow, or it would slow it down because the density of mercury is higher. We'll talk about that. Hopefully you'll be able to hear it in about a slide and a half. If you have questions on it, we'll go through that as well. Finally, since you have density, you can also calculate volumetric flow. So if your application, process, or recipe requires an actual volumetric measurement as opposed to a mass flow measurement, the Coriolis mass flow meter is a very good volumetric flow meter as well. And it actually provides real-time volumetric measurement because you're getting the density divided by the mass in real time. So there are no fixed values. So your values are very representative of your actual flow. So in short, when you get, I don't know if you can, oh, well, I didn't want to go back there. Let me get you my little pointer here. Okay, so when you buy, boy, I'm the worst artist in the world. When you buy one of these, you, at the same exact time, get a regular mass meter, a volumetric flow meter, a temperature sensor, and a densitometer all in one from one device. So that's one of the benefits of that Coriolis. Of course, now I can't go forward. Bear with me, if you would. All right. Isn't that nice? This guy actually got to stay in there. Hang on, let me remove that. All right, so this is a 3-minute video, and it details what Coriolis does and how it does it. It is extraordinarily good for such a short video, but we will be discussing it pretty much in detail once it's over. So without further ado, here's the video.
Unique design, peak performance. The Siemens Citrans FC430, a pioneering Coriolis flow meter. With the Coriolis effect, a physical force is explained. It acts on a medium that is accelerated in a rotating system, like a ball on a rotating disc. Its movement is straight. However, if the observer turns with the disc, the ball is apparently deflected. The same effect occurs with a water hose that rotates around its own axis, like a skipping rope. As soon as water flows through, the hose also twists. The effect also appears with an oscillating movement. The twisting is stronger or weaker, depending on the amount of water flowing through the hose. This effect allows the mass of liquids or gases to be determined. The Siemens Cetons FC430 flow meter functions according to the same principle. Two symmetric metal tubes are set vibrating. This is ensured by a driver coil in the central section. The tubes oscillate with a resonance frequency, similarly to a tuning fork. The oscillation is measured precisely by two pickups at the inlet and outlet sections. If liquids or gases now flow through the tubes, a phase shift occurs, as with a water hose. The pickups measure the spatial and temporal displacement. This determines the amount of liquid or gas flowing through the tubes. The greater the amount, the stronger the tubes oscillate outwards. Siemens presents yet another Coriolis device for measuring mass flow. Thanks to the precision of every detail and its compact form, the Cetons FC430 represents a small revolution. A multi-parameter flow meter with maximum reliability. In addition to the mass, it determines the density of a medium. Denser media have lower frequencies. Put otherwise, water oscillates at a lower frequency than air. From the measurements, multiple parameters such as volume or concentration of substances in a liquid can be derived. Data and results are stored internally and on the innovative sensor flash. They are available at all times as backups, just like the audit trail function and all certificates. Unique design. Peak performance. The Siemens Cetons FC430. Designed for excellence.
In short, Coriolis flow measurement in its simplest forms is basically like a scale in the bathroom. You step on a bathroom scale, the scale compresses against the spring moves the needle that says how much you weigh. Now the Coriolis flow meter does essentially the same thing. It works on the same property that says things in motion stay in motion unless acted on by an outside force, and things at rest stay at rest unless acted on by an outside force. So imagine, if you would, I know you couldn't hear the audio, but if you remember the picture, there was a vibrating tube there. Now when a tube is vibrating, okay, and fluid enters the tube, the fluid that is entering the tube is not moving. It is not vibrating. It is on its own, in its own plane of motion, not in a vibratory plane. So what happens to the vibrating tube when it contacts the non-vibrating water is the tube itself slows down. Now what happens as that fluid that is slowing the tube down travels through the tube is the fluid pushes on the tube pushes on the fluid, and the tube slows down, but the fluid inevitably begins to move. And as it begins to move, it picks up momentum. Then by the time the tube is ready to vibrate the other direction, what happens is the fluid continues on the path that it started when it entered the tube. So now things are in motion and they don't want to stop. So what happens to the tube on the outlet side is it continues in the direction of vibration. Okay, so in short, in a quick review, when the fluid enters the tube, the vibrating tube, the tube's side, inlet side, slows down, while the outlet side actually accelerates. So what happens to the tube is the tube starts to bend, okay, because you have a slowing on the inlet side and an acceleration on the outlet side. Now, what does that mean? Well, when there is no motion of fluid through the tube side A and inlet side and side B, outlet side, they are vibrating in unison. When the fluid starts to move through the tube, because the tube is slowing on the inlet and accelerating on the outlet, and it's bending, the inlet side and the outlet side are now out of phase. So what happens is that we hang little magnets, little coils, on the tube, and as the magnets and the coils move into one another and out of one another, they generate an AC voltage. That AC voltage is carefully monitored. And what happens is that when there's no flow, the voltage curve from A and the voltage curve from B are the same. In other words, the right side and the left side are moving up and down at the same pace. When the fluid starts moving, that pace varies. So the inlet and the outlet are no longer in phase. That phase difference is directly proportional to how much bending there is in the tube. And that amount of bending is directly proportional to how much liquid or fluid, it could be mass, whatever, it could be a solid, is moving through, how many pounds are moving through the tube. The more pounds, the more bend. The more bend, the more offset. The more offset, the more time difference between the right side and the left side. And that's what we're actually measuring. Now, as far as the density goes, okay, as far as the density is concerned, the faster the tube is vibrating, the lower the density is in the material in the tube. Because an emptier tube or a lighter tube will vibrate faster, a heavier tube will vibrate slower. So that's the density. So that's the summation of the video. So we've now taken 6 minutes of our 30 minutes or more, I don't have a clock here, or more, going over this. Now, this slide pretty much dictates what it is that is at the heart of Coriolis, in that in this side we have flow. Let me get my no pointer here. So on this side, we have flow. We have a tube vibrating, but A and B are the same, right on top of each other, so there's no flow rate. As soon as you get a flow, A and B are out of phase, and it is the phase difference that we're measuring. So the big secret for Coriolis: things at rest stay at rest, things in motion stay in motion, and that's how it works. Everything else is all electronic wizardry. Okay, that's the mystery there. So whether I'm measuring helium or whether I'm measuring asphalt, doesn't really matter. Even molten sulfur, it all obeys the same laws. A pound is a pound is a pound. All right. So with Coriolis, because of the way it works, there is no compensation necessary, as I mentioned, for temperature or density changes in the flow. It doesn't really matter. You can use the same kind of meter for gas or liquid. You can use the meter that you buy to measure water or helium. Same exact meter. Doesn't really matter. You don't have to change the meter out because a pound, of course, always weighs the same. And again, measuring more often than I care to, Coriolis is not affected by process fluid characteristics. You don't need any straight runs. Okay, viscosity is not a problem. If you can push 4 million centipoise fluid through your meter, you can measure it. It may be a pressure issue there, but of course you can do it. The meters are typically extremely easy to install, usually plug and play in PLCs, DCSs. Most of them have pulse outputs for analog or 4 to 20 if you want to use that. There are no internal mechanical parts to fail. It's basically a pipe, and the vibration that the pipe does is extremely small. The devices, once installed, are very stable long term. Once you zero the meter and the parameters don't change, it's pretty much a set and forget it. Another advantage to Coriolis is the turn down. You know, we hear 100 to 1 turn down, not a big problem. If you're measuring 100 pounds an hour, you can easily measure 1 pound an hour. Well, with a Coriolis meter, it's so accurate and so linear, 250, 500, or even higher ratios are not uncommon. So you buy one meter to measure an awful lot of different things in a lot of different applications. Lastly, one of the newest benefits is the small size. Some of the newest meters are incredibly small for the pipe size that they go into. And the reason mass flow is important is all the reasons I mentioned before, is that you don't need any changes, any adjustments, any corrections. But if you're measuring a fluid, such as oil in this particular example, if you fill this barrel up to the very brim in the morning in a southern Texas oil field and you don't put a lid on it, by the time afternoon comes along and the temperature's gone from 40 degrees F to 105, you're going to have spillage because you have expansion of the fluid. Mass is not affected by this, and that is one of the key benefits of Coriolis. So that's the overview of Coriolis technology. This is a fairly short review, so I apologize. If you need more information, please don't hesitate to ask either a question or the reps afterwards for further input. This is one of the newer technologies in Coriolis. It's called an FC410 because that's what Siemens wanted to call it. But the big deal is this is yes, sir?
Before you get into that, can I throw a question at you?
Please.
Is the driving frequency of the meter dependent on the fluid density?
The driving frequency is dependent because what they're trying to do is what the meter is trying to do is driving the frequency of the tube to its resonant frequency, the frequency with which the tube naturally wants to vibrate at. Everything has a resonant frequency. Every vibratory structure does. Now, a tube filled with air has a different resonant frequency than a tube filled with water. And a tube filled with water will have a different resonant frequency than one filled with, say, liquid mercury. I just keep picking that because that's one of the denser fluids I'm aware of. So what happens is that as the tube is filled with ever-increasing densities of fluid, the resonant frequency of that particular tube goes down. The tube is more comfortable vibrating at a lower frequency. So the density of the fluid affects the resonant frequency of the tube that it's in, and the resonant frequency is achieved by that frequency with which the tube naturally wants to be at, actually where the power to drive the tube is least for maintaining a stable frequency. I don't have a direct here to see whether or not I answered that question appropriately. So did I answer that question appropriately? Are there any other questions?
There are no other questions. If you didn't answer it appropriately, whoever asked the question, feel free to ask further so that we can clarify it.
All right. Happy to talk about that for about 4 or 5 hours, so don't worry about it. So as I was saying, this is one of the newer kind of small, this is a half-inch tube sensor. It weighs about 10 pounds and is about 10 inches long, so it's an extremely small meter. This particular device is also digital interface, so what that means is as the information comes off the tube, it goes directly into an analog to digital converter, and then everything from that point on is all communicated via Modbus. So there is no display, there are no push buttons. You interface with this with a either 4-wire terminal block or a quarter-turn 4-wire class 1 div 1 terminus, and it makes for a very quick and very easy interface. And if you're using Modbus, it's pretty much a one-click go. As I said, this is one of the newer ones. Other devices still do the 4 to 20 that we sell, still do the DeviceNet, HART, of course, is still available. It's just this is one of the newer ones that we thought we would highlight. So the process variables in this guy, of course, mass flow, volume flow, density, and fluid temperature are still standard and available. The update rate, the data is pulled off the meter 10 times at 100 hertz. So every 10 milliseconds, you get data when you need it. Now that's not the frequency of the tube. That's the update rate. So as your fluid rate is changing very quickly, you can pick up the data at 100 hertz. It's a pretty fast update rate. Now the tube frequencies, since that question was asked earlier, I mentioned the tube frequencies can vary greatly depending on what's in them. But the tube frequency, the highest one on our device is about 700 hertz, and the lowest one is about 350. And the reason for the higher frequencies than some of our competitive meters is we find that these frequencies help mitigate some of the process noise that are typically seen in the industry in the world today. I see we're running tight on time. Yep, go ahead.
We have another question.
Yes.
Pipe warp. Does piping torque affect the accuracy?
Fantastic question. You're falling right into my trap. Very good for asking that one. Okay, so in the installation of the meter, I can see we're going to run long now, so I'm warning you now. In the installation of a Coriolis meter, the very simplest answer to your question is absolutely. Yes, definitely. There are 3 types of stresses that can affect the performance of a Coriolis sensor, and those are compression, squeezing of the meter, tension, stretching the meter, and torsion, which is what you were talking about, the twisting of the meter. What ends up happening a lot of times is even a perfectly installed, properly installed meter with hard pipe will become pretty much entwined in miles and miles of piping that grow in length and change and shrink in length with the heating and the cooling of the process. So under those conditions, in the morning, if the device is at 40 degrees Fahrenheit, in the afternoon it's at 150 degrees Fahrenheit, and there's 4 miles of piping in the plant, that pipe has probably grown 6 or 7 inches. And if it's all squeezing on the meter, you can actually have what's called a zero drift. Now, it hasn't changed the accuracy of the meter, but what it has done is it has changed the offset. So if you're not flowing anything, the meter can think it's flowing 5 units of flow or -5 units of flow. And the same thing happens in reverse in cooling. If the meter is installed when the pipe is hot and then the pipe's cooled down, you're stretching it. But by far the worst one is the one that was mentioned in the question, the torsion. If you have class 150, 300, or 600 flanges and the holes don't quite line up and the sensor is twisting, those forces of compression and tension are amplified through a torsional effect. That's the nature of Coriolis meters. In order to combat that, as I said, you have fallen into my trap. In order to combat that, in the design of this meter, let me put my little spotlight back on. This section right here, this is the main support structure. This is our smallest meter pictured. It's a 1/4-inch tube. This section is 304 stainless steel, and it is over 1/4 of an inch thick. So what it was designed for is to take incredible forces from the inlet to the outlet and transfer it directly straight through the case, not affect the tubes that are underneath. So what they have done is, in the design of this meter, is mitigated that particular problem. You can never really eliminate it 100%, but that was a great question, and the design of the sensor was designed in order to help deal with that very serious, very particular problem, the Coriolis meter. What I was talking about when I started this slide was the digital stuff, and I'm going to go quickly now because I can see our time is almost up. The design and the consideration for digital communication was done to reduce noise, to allow for a faster data update rate, to make it very quick and easy for a device change-out, process connections, one-wire connector. And of course, since it's so small, this sensor could fit more units and units period, more of them, where some of the competition cannot quite squeeze in. Though some can, some are very good at it. One of the other benefits that has come up is, since this is a dual tube meter, meaning there are 2 inlet ports within this device. If it's a 1/2-inch meter, there are 2 1/4-inch meters. This Hemi-shaped inlet port, yes, it has a Hemi in it, helps keep the process quiet. It was originally designed in order to allow for a 3A sanitary approval, but what they found is that when they were doing that, they had no dead zones for anything to hang out, and it created an extremely quiet flow profile. That extremely quiet flow profile aided in a very, very good signal-to-noise ratio. So at very, very low flow rates, when you want the flow to be very quiet, this particular inlet port helps do that. It also is very gentle on the flow. If the flow cannot be mixed, the inlet port, the Hemi-shaped inlet port, is very gentle on the flow, does not cause a lot of turbulence, which means it doesn't affect noise. In the oil and gas industry, this is a big deal because of buildup of waxes and paraffins. Creates an extremely stable 0 point, and on and on and on. It also provides a very low pressure drop, which is great because it's a two-tube meter, and we find that the pressure drop on this dual-tube meter is even lower than on some single-tube meters because the pipes themselves are extremely short.
All right, Eric, we've got a few more questions.
All right. Well, I'm going to skip this slide then. Go ahead.
Well, you can just hang out there for a minute.
Go ahead.
Does installation orientation need to be specified up front? Does it affect,
it does not.
Does it affect calibration?
No, not in the least. Whether you have a pound upside down or a pound right side up, it doesn't really matter. What does matter is when you install it, considering what it is that you're flowing. These tubes have low spots and high spots. Now, you can set them up in a self-draining condition, but you can see that in the tube, and I'll actually go back to this guy. This is in a position in which you would be flowing liquid. Okay, so if you're flowing a liquid, you've got to bear in mind that you may have gas particulates in the stream, and that's the way the flow goes, like this. So you wouldn't want to mount this tube either like this, or turn it so you're flowing up through the meter so all gas bubbles can mediate out. If, however, you were flowing gas, your problem then becomes liquid collection, in which case this meter would be inverted and the hump would be facing the ceiling as opposed to the floor. So you don't need to specify that when the meter is purchased because you just mount it any way you want. It does not affect the calibration in the least. But you do want to bear that in mind when you're installing it.
Would you ever mount it horizontally so the tubes are horizontal?
You mean basically so that the bump is facing the walls? So that this would be facing the walls? Oh, yeah. Yeah, there'd be no reason not to do that. There's nothing holding back from doing that. If you could only fit it in that position, and as long as the only consideration would be is that you have two tubes in there, and if you're flowing a liquid, you would tend to have bubbles collecting in the upper tube. And if you were flowing a gas, you would have liquid collecting in a lower tube. It's a consideration. It's a risk, not a big one, not a major concern. But you can surely, as long as you can keep the flow moving, keep the air out where the air needs to be out, and keep the fluid in where the fluid needs to be in, or the fluid out where the fluid needs to be out, you can surely measure it horizontally. Absolutely.
Okay. Next question.
What else? Yep.
Since the Coriolis meter uses smaller tubes, is there pressure drop data available for specific fluids?
Absolutely. It's not a table. It's actually a program that you can get from the representative who's running this, hosting this particular thing. It's a program, and what you would do is you would actually input the viscosity of the flow that you have, the flow rate that you have. It's always nice to have the temperature and the density as well. You put all that data in, and you can change the tube size and see how it affects the pressure drop. I don't even know. We don't even need to know what you're flowing. Just put in the viscosity data.
That's all the questions we have for now.
All right. All right. I've been warned not to go long, so I can see I've already ignored that request. All right. Talked about this. I'm going to skip that. All right. So the fundamental design of the new Coriolis meters is to make everything as easy as possible. Now, there are devices that we have that have displays that make the regular installation without a PLC or a DCS very simple. It's all wizard-driven with on-screen menus that walk you through what to do for first-time setups. Like I said, the newest of the new is this digital interface for Modbus, which you plug into your DCS or your PLC, and you kind of turn it on, find the units, and set your limits, and you should be good to go. The greatest benefit there, of course, is that if you pull one of these units out for service or recal or whatever it is you want to do, and you put another unit in, the programming is still there, so you do not have to reprogram. And even if you had a competitive meter, if there was a competitive meter in an installation such as this, and because of this webinar you decided, oh my God, I got to have Siemens, this presentation was so great, and you decided to pull out the competitive meters, the programming is the same. So if you had somebody else's meter in there running on Modbus, their registers and where their data is stored and how the data is called up is the same. That's kind of nice. This is the local user interface that I was just talking about. If you aren't using Modbus as your digital interface, and you want to use HART, or you want to use 4 to 20, or you want to use pulse outputs, this is the type of display that you would get. Now this is a very, I know I said very too many times there, flexible display. You can show, as you see on this display, you have a flow rate, you have a graphical representation with 0 being in the middle and negative and plus. This is also showing the density and the fluid temp. Now this single display can show a single value in 2-inch long block letters with backlighting, so you can see it in total darkness from halfway across the room. You can also see 8 variables: temperature, totalizer 1, totalizer 2, density, volume, all on one display. Makes it very handy. We've also just added this type of graphical representation where, if you would like to, you can have your flow rate displayed and then your flow rate over time, or your density over time, and this can be a graph that you can set up that will actually display directly on the screen. Makes it very, very user-friendly. Of course, many languages, including Spanish, can be programmed into the device. That was a big question in my last presentation, which was in the Texas, Arizona area. And you can do digital inputs to reset to 0, or reset the totalizer, or start-stop batching, etc. I'm almost done. Every time I turn on that little red dot, I have to go back and turn it off, so future note. Almost last but not least is a audit trail function within the device. If your device is installed and you want to make sure that people or lab tech or whoever you have out there are not messing with the device, every change and every interface with the device is logged. So in this particular case, you can say that somebody went in, this is who went in because it's the password they used, and they changed from English to German language. So, you know, if there's a problem and something changed, you can see when it was done and almost who did it. Heating jackets are available. They are custom made to fit our meter, so there is no need to have additional heating jackets made if your application requires heating. This was a big boon to a lot of customers because you can get the jacket with the meter. Once installed, sometimes it can take 4 to 5 weeks to get a heating jacket made, or longer if it's a very specialty made meter. I had a lot more applications, but I'm going to cut this one short. It's one of our newest applications, which is a fuel flow management aboard ship. There is a United States company that manufactures the bulk of shipping fuel management systems, and they evaluated Coriolis meters, our Coriolis meters, as the meter to use specifically because of its noise abatement, its low pressure drop, its small size, its digital interface, pretty much everything I just talked about. These were things this particular customer were looking for. So there were actually 2 slides on that application, but I'm going to skip the last one because I can see that only leaves 5 minutes for questions. So as I said, my name is Eric. I'm at Siemens in Springhouse, USA. You can ring me up at the number you see there if you have further questions. And that is actually the conclusion of the fixed presentation. Unless you guys have more questions, I'll be more than happy to entertain them.
More questions.
I have more answers.
All right. If using 4 to 20 milliamp as your communication, how many outputs can the transmitter send?
4.
4. So can you have flow, temperature, and density? All
yeah, and yeah, you can have all 4 to 20. You can have your mass flow output on one, volume flow output on one, temperature output on one, density output on one. You can also do some on 4 to 20. You could do one 4 to 20 and a pulse output and a digital input and then a relay or 2 relay. There's a variable cornucopia of options as far as the 4 I/O functions.
All right. I did just send out over the question taskbar the link to YouTube for the video. There's 2 other ways you could get at it as well. If you just go to Google and type in Siemens YouTube channel Coriolis, it will come up. Another way you could get at it is type into Google, think Siemens Coriolis, and it will come up as well. Here's a good question for you, Eric. How does Siemens compare to Micromotion?
Well, Micromotion is a phenomenal product. They have an extremely extensive line and a lot of variability. The product that we're talking about today and the majority of the products that we sell compete very favorably with their elite line. That would be the CMFs and the F series. So those would be the upper part of their high performance line. Their elites being one of their highest performing, and the Fs kind of being the next grade down. So as far as performance goes, it's almost a one-to-one. The performance is the same, 1/10% of rate. The variability of the fittings are essentially the same. There are some small differences. Our sensors are a bit smaller, a bit lighter in weight, a very small difference, of course. The immunity to noise really is very dependent on the application, but the Siemens sensor was designed to mitigate that with a series of design changes as well as electronic filtering, and we also considered that when picking the frequencies with which our tubes vibrate. Our tubes are very, very small, short in length, in other words. They offer very gentle bends, providing very low pressure drops. So the reason I can't give any absolute answers is the pluses and minuses are usually very application dependent. I can't say Siemens Coriolis always offers lower pressure drop, but oftentimes we do. But a lot of that depends on the fluid. As far as accuracy goes, essentially the same. The big question on everybody's mind, which everybody's probably saying, well, you say it already, is pricing. We will be less expensive under normal pricing conditions than their CMF or their elite line. We'll be comparably priced, or maybe 5 or 10% less than the F series line. So I hope that answers the question. I could go on for another 2 hours on just that, and then there's Endress, and then there's Corona, and then it goes on and on.
There is a question here: which Anderson-Hauser models would we most closely compare to?
83F. It's astounding how close it is. I think they used it as a benchmark. 83F by Anderson-Hauser is a very, very good Coriolis flow meter with a lot of functionality. Not quite as much as of course, as the Siemens has, but we just came out with it, and the 83F has been around for a while. It is a good sensor, but it is also, and there's no downside to it. It is the closest meter to the Siemens meters. Again, a lot of the variations in performance kind of come down into the small things, how easy it is to set up. People have said, of course I'm biased, so you take it with a grain of salt, that the Siemens is probably one of the easiest meters to set up, especially with the wizards. The functionality of the display and the information you can get right off the display without having to input to a HMI or a graphical interface, separate graphical interface, is pretty much second to none. The programming of the device in the event of a failure, if you get hit by lightning and the transmitter goes away, all the data that you had stored on the device is actually stored on an internal memory chip on a micro SD card. So that information of the calibration data, the calibration cert, the sensor cert, the material cert, maintenance records if you want to update it, are all stored on a micro SD card. The audit trails, all that. You pull that micro SD card out, assuming it isn't melted in the lightning strike, you can put that in the new transmitter, hook it into the new sensor, and you're ready to go. And in the event that the micro SD card is also toasted, you can take your digital phone, your iPhone, or your whatever digital phone du jour, scan the QR code on the outside of the meter, and get all of the calibration data from that sensor direct from the network through our servers, so that you can update your system in the field without having to contact your representative or Siemens. So you get your calibration data right there. So that's kind of handy. These are all some of the little things, but we are very comparable to the F-Series in Micromotion, very, very comparable to the 83F in Endress. What else?
How does the meter react to two-phase flow, air into liquid,
they almost answered the same. They almost answered the question in the question. Okay, so what happens in dual phase flow is, say for example, you're flowing water, and the water has entrained air, and you're flowing 20% air, and the rest of it is water. Well, what happens to the meter is nothing. It's a piece of pipe. It doesn't care. But what happens to the output is it jumps around a lot. Now, if the owner of the meter recognizes what's going on and says, hey, I got 10 pounds a minute, hey, I got 100 pounds a minute, hey, I got 2 pounds a minute, hey, I got 1,000 pounds a minute, well, you're basically spitting through the meter. You have some fluid and some air, and you're going to get an unstable flow. Now, there are ways to mitigate that with how it's mounted. There are ways to mitigate that with internal filtering, time constants on the output to try to smooth that if it becomes a problem. The meter itself really simply just doesn't care. You won't get a good accurate flow measurement because you're changing too fast. Now, if you have what we like to call a homogeneous mix of water, or any liquid in this case, and air, but it's homogeneously mixed, it doesn't care at all. There's no problem at all. So imagine, if you would, a nice solid stream of water with little air bubbles all throughout it, evenly dispersed. The meter will simply read that as a fluid with a density less than that of water, so 0.7 or 0.5 or 0.4 grams per cc as opposed to 1. The meter won't care because it's still going to measure the pounds. And it only becomes a problem for very, very slow flows where the fluid and the air have a chance to separate. And in the question, he actually had the answer, or she actually had the answer. What happens is that in time, as the flow continues and you push the air out and you just get the fluid, then the flow will finally stabilize. So in the end, the meter really doesn't care. Your flow will be erratic until you clear the lines of the air. So that's the answer to the question.
Okay.
What else?
Next question. In the world of pharma, they need consistent model numbers. I'm assuming because of validation. What's Siemens' approach toward keeping their model numbers the same, or how often do they change them?
Well, that's a very loaded question. Let me answer it. Two completely different answers with the same sensor. We're selling a meter now, the 2100 series, which we didn't mention during this presentation, that has been in production for almost 20 years. Its part number hasn't changed in 15 years. Okay. Now, just because that has happened, that's no guarantee that part numbers are never going to change. Companies always have and always will add and subtract products from their offering. But Siemens usually sticks with them for quite a long time without modifying them. Now, we had the FC430, which was the display unit with the display, and that's still available, even though we just came out with a new model, which is the FC410, which is the Modbus version without a display. So the part numbers stay fairly consistent for quite a long time. We have one customer using one of our smallest meters, 1.5 millimeter size tube, for almost 21 years. And they've also standardized on it, which has been a boon to them.
Good. Eric, believe it or not,
yes,
that's all I have for questions.
All right.
Unless one sneaks in here very quickly. Eric, I'd like to thank you very much for your presentation. If anyone in the audience does have any specific application questions, feel free to give us a call at 800-9-LESMAN, 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. At this point, there are no further questions, so we do plan on concluding the webinar. Again, thank you, everybody, for attending and taking time out of your day.
Thank you, everybody. Take care. Call us if you need us.
Thank you, Eric.
Thank you.